Hello, welcome to the Barbaric channel. Um, Before I start, uh, everything I'm covering here you can find on my website. So uh, here's my website. You can go and have a look. There's uh, quite a few pedals so far. Uh, Following this, articles link, you have a really quick overview what I've been working on. So have a look. But for today, well, what I was thinking, I was watching the other day uh, something on YouTube, that pedal show, I think, and that there was like they were saying there were three. What would be your first three pedals? So uh, they were saying I probably distortion, well, overdrive, fuzz, whatever, whatever you prefer. And then the second should be modulation effect, and third the time-based effect, a delay, for example. No, this is a matter of preference. But that made me think. I did lots of boosters and distortions, and I did fuzz, and but I didn't look into anything other than that. So maybe I should look into modulation, for example. Like modulation are things like flanger, tremolo, wah, phaser, vibrato, chorus. There's loads. Um, I should probably start with something simple, I suppose. Probably one that I can understand to a greater extent and build. And one of the simplest of them is a phaser, and like this phase 45, for example. Um, they were all rage, 70s and 80s, like they were like huge. Everybody used them, and all kind of styles, like from Pink Floyd to Van Halen and beyond. Like Jimi Hendrix, etc., etc. So everybody use them, and they're super popular today as well. There's all sorts of variations there. How What is this effect? Well, you know uh, it shifts phase. So as its name says, but what does that mean, and what does that gives us? And this diagram shows it the best, I think. There's this what's called all pass phase shift network. So what it does, it just passes the signal. It doesn't uh, uh, amplify or attenuate the signal. It just shifts the phase. Okay, so this is, for example, that one of those uh, networks. We'll call it stage. That stage doesn't really affect the sound on its own, because humans really can't hear that phase shift. But this, but when it's combined with a dry signal and your phase shifted signal, if we think about it as a pure sinus function, if you shift it by its phase 180 degrees, like it kind of cancels each other. So if we do something clever and like move this, we change where this cancellation occurs, we can kind of shift up and down uh, this sound, like some kind of a sweeping sound. Okay, so so what we'll have some kind of a dry signal coming in, and then we're going to combine that signal with this phase shift network, and it's going to be interesting. It we will need uh, we will need two of those stages, and this is how many phase 45 has. It's a simple pedal. It has only one knob that controls the speed of this kind of a at which frequency this phase shifting is occurring, and has some effect, because this phase shifted on its own, we won't hear a difference, but when it's combined, it interferes with the original sound and gives us a nice uh, sound. So uh, let's look into schematic. Okay, well, where do I have it? I have it here. So this looks a bit complex. There's lots in it, but you know before I continue, I have to say I did some modifications, but let's get into details of different parts of it, because lots of it is what we've seen before. So here I had to change some of the parts just because what I had lying around. So it shouldn't make any difference to the sound, but I just it's important to say, and I'll call them out a bit, but let's jump into this. First part is we have this input stage, and then we have this output stage, which is also a mixer stage. And this input stage is, we've seen this before, like standard stuff here. I slightly adapted this. So, I add this resistor, it helps with popping sound when you switch the pedal on and off, helps. The input is just a buffer, helps with the signal, preserve the signal, helps out with that. But uh, it sends, this is the dry signal, it sends it to this output stage where this is common emitter amplifier, simple one. PNP is used here just because it's easy to bias it, without going into more complication. Uh, it's standard stuff. This output stage also serves as a mixer because here we have dry and wet sound mixed together. Now, this is different from the original pedal. Uh, Original one has it other way around. The original one has amplification here, a slight gain, 2 times gain at the beginning, and has passive mixer at the end. I just used P90, phase 90 way of doing it, more or less. I changed some of the resistor values here. For example, I used 47K. It was a bit different value here. It doesn't really make a huge difference since we're talking about just slightly more gain here, nothing much. But other than that, doesn't affect the sound. So this is pretty much the same as how P45 works, slightly different components, but in reality, it doesn't really make any difference to the sound. The power supply is slightly different. So here we have this power supply section. If you think about it, we will use JFETs at some stage if you look at here. So they need to be biased as well, and we need reference values for our op amps. So that gives us two sort of reference slash bias voltages, where normally we had only one for op amps so far. Zener diode gives us reference value at around 5 volts. And then for biasing, because JFETs vary wildly in their specification, we have this trim pot here to try to get that bias point to the right voltage. Original has 250K trim pot. I have 100K, I don't have 250. Won't make any difference because it is just used as a voltage divider here to get us the correct bias. Okay, so hopefully, I'll get that JFET thing a little bit later, but this so far there's no mystery here. It's pretty standard stuff in the pedal. Now we move on to a bit more interesting parts. So this is a low frequency oscillator, LFO. The purpose of it is to speed up or slow down the movement of this frequency where this phase shifting occurs. So we get that sweeping motion. So if I go back to this diagram here, there is a diagram what it actually does, what these stages do in frequency response. They create this kind of a notch where these frequencies cancel out. So input dry signal and wet signal. And what we want to do is move this notch left and right in frequency domain. So we go higher frequency, lower frequency. That sweep causes that, you know, like moving sound. So this is what does it for us, you know, this oscillator, and this speed pot controls this speed. It goes to up to kind of a relatively quick, like wobbly sound, and then very at the highest or lowest setting, it is very slow sweep. Still, you can hear the difference, you know. So this one in particular is combination of it's this is Schmidt trigger oscillator with, you know, using Schmidt trigger, and there's this integrator here. It's fairly part of it is fairly standard. Funnily enough, this Schmidt trigger based oscillators are even used in lots of modern microcontrollers when you know, you don't need to use external crystal for, you know, generating oscillations. So it is very, you know, relatively well known circuit, but let's see how that actually works. I prepared spice simulation for this. So here is the oscillator, and I actually have full thing here, and I'll upload it on the web page. But just I'm going to focus on this part here real quick. So how this Schmidt trigger works? If you have input that let me run this actually. So let's see. Let's sample output and input. And input, I just have a sawtooth signal. So the signal just goes up to 9 volts and back as a triangular signal. When it goes up, because we are using inverting input for this, it's kind of a in different phase, but doesn't really matter. So when we look at here, when it goes up, it changes. Oh, actually, I should use this one. It goes all the way up. When the input goes all the way up to, what is it, 5.9-ish volts, the output drops. It goes down, and then it stays down until our input starts coming back, and then when it comes back, the input, this blue one, when it comes back, when it passes threshold 4 or 5, roughly speaking, it jumps up. So it's kind of a, if you think about it in the digital world, this would be 0, this would be 1. So if you have a noisy signal, you know, and then it goes up, it kind of that's the purpose of this Schmidt trigger, because that's how, you know, you get stable state changes. But in this case, what it gives us this hysteresis, or it's, you see, it's not symmetrical, this switch of the change of the level going up and down, you know, low and high. So you would expect it to be somewhere at 4.5 here, somewhere in the middle, but it doesn't happen in the middle. Just the switch happens here and there. So we have this part here where it's stable in between these two, where, you know, not thing stable. This is where this change is detected. Okay, this is important because then we can use this to create our oscillator. Okay, let me just remove this. So I'm just going to delete this one. So if I look at just this part here, and I made oscillator here out of this. Let me zoom in. This is just how to create an oscillator with Schmidt trigger circuit. So when it goes high, when the output is high, this capacitor is charging. So if you think about it, if you remember that, that's the part where this input between that threshold part. So now we are, for example, it's high. So as the triangle or that input, if you remember, goes up, this is actually charging. It's charging through this resistor. This capacitor is charging, and then when it reaches that threshold, the output goes down. So now our capacitor is discharging, and then the signal is. So what we get here is actually that triangular input that we saw just earlier. That's how we get this oscillation. So let me run this, and you'll see what I thought about it. So this is output, and this is now our input. All right, and I did see here 10K. This is very low. If you remember on the schematic, and I kind of in the original one is 4.7K or something like that. So this is where you control the highest frequency of this. So you can change this. It doesn't really matter. It depends. It's up to you how far you want to go here. What's the highest frequency you want to get? But at the top end, it goes to 500K. So this is where this speed goes. So in this one, this would be the highest frequency. You see, it's frequency goes relatively high. I don't know what is this. This is the period is 0.1 seconds. So what is that? That's 100 hertz, is it? No, I'm going crazy. It's 10 hertz, isn't it? Yeah. So it goes that far, but if you start, increasing this, so this is what I was talking about. And if you remember, this is very indicative where it goes. You remember that threshold part where I said the the Schmidt trigger is triggered. It's around here and there, So in between that part, we have this charging and discharging of the capacitor, and that's what kind of powers that Schmidt trigger to change the state, etc., etc. So this is our oscillator, and if we increase this, say 100K, what did just happen there? I should have named this. So I'll run it again. Now when I click here, it won't go crazy on me. So you see this frequency changed. If you remember previously, it was really, there's lots more of these on the page. They were more dense. Here we have this is from here up to here. That's, I don't know what that is. 1 hertz. I'm just, let's call it 1 hertz. But and as we increase, this goes, you know, slower and slower, lower and lower frequency. But something interesting happens here. It doesn't start straight away. And this is because the current here is small, lower and lower, and hence this initially discharging of the capacitor is slower. I suppose that's where this, you know, we add this, and I'm not 100% sure about this. This is like me. I'm not really an expert in this area, but like if we add this integrator here, we're going to solve that problem. So let me move this. It looks like shit. Pardon my language. I might cut this out. Add this out. Okay. So remember how this looked like? It took a while. And if I went all the way to 500K here, that would have been like, it would go off the off the diagram, which is 10 seconds, you know. Why is this showing here? This is going to be embarrassing because I might show different. Ah, yeah, it's the same thing. So that's really it. So when I added these two components, this is exactly what our oscillator now looks like. It starts working straight away. So that's what I think this is used. Don't hold me to it, but I'm pretty certain that's what it is. And if I look at here, if I plot this, I'm just going to remove these first two. We get the same thing. This is at 90% rate. And if I change the rate to, say, 10%, yeah, that was long, right? That was long explanation. So, but you got the point. So let's move on then. This is not the most important part. This is, you know, if you want to do something about it, there are things to change. I didn't use exactly same components. I didn't use, there was 15 microfarad here capacitor. I had 10. It will work, you know. So, but this is really only affecting frequency. Now we're going to get to that part where, you know, this might affect your biasing point, because if you it affects biasing to a certain extent, the value of this resistor, but I only had 3 mega ohms. Original has 4 or something like that, 3.9. So essentially it should not affect the sound, but it does affect biasing point to a certain extent. Anyway, this wasn't that important. The most important part is this. And this is our 2 stages. So this is one stage of that phase shifting network. This is second stage. These JFETs here are really used as variable resistors. So I'll pause talking about them just for a second, you know. So let's see how does this look like in Spice, for example. So I added sinus wave here. It's entering this network here. Let me zoom in. And I just named this phase shifting in, phase shifting out. This doesn't really matter. This is the whole point is to get a plot that will, you know, demonstrate what this does. And if you look at here, I have 6 stages, okay? 6 stages, but I'm just kind of wiring here rather than using all 6. So how it's wired now, I have 2 stages wired up as P45, okay? So if I run it, and what I'm first going to look at, I'm going to look at one stage here, right? So this doesn't give us a good, so this is how to plot it. And ignore this, this is really, we are talking about milli, this is just Spice doing his thing, you know. This is 0 dB, so this is no amplification or attenuation of our signal, so it's really 0. If I get a better resolution or something, might show a bit different. So I'm just going to remove magnitude. We don't care about that for now. We just want to see, this is our phase shift. So to have any effect, we have to shift phase by 180 degrees. So what the hell does that even mean? You know. So what is this? So let me show you here. So this is, if you look at here, you'll see what is the phase shift. So if I say 90 degrees, this is happening. I can't really get it. Okay, about 337. It's 338 hertz is happening. This 90 degrees shifted. Remember this. This is important because this is where we're gonna expect this notch to happen in frequency domain. We can't, with one stage, we can't move the phase 180 degrees. You know, whatever we do. So we need at least two of these stages in order to get different frequencies are shifted differently, you know. So in this case, only frequency of 338 is, oh, if I can get it, is shifted 90 degrees. For example, 522 is shifted 66 degrees. And if I go here, 138 is shifted 135 degrees. You know, so different frequencies are shifted differently by different number of degrees. So we are talking about 90 degrees shift. So we need 2 stages, right? As we expected, because that gives us 180 degrees. Now, this is because we are using same stages. You know, they're the same with the same this, you know, phase shifting function. If we could use different values here, but then that phase shifting would happen at like 80 and 100 degrees. Maybe the same frequency would be shifted by one, would be shifted, the same frequency would be shifted by 80 degrees, by the other one 100 degrees. That is still gives us 180, but we'll just go. I can't even maths for this. I'm just using LT Spice. That's how much I know about this. Maths is just not, I'm not really great with that. But what is the output of these 2 stages? So remember that frequency earlier? And this time I'm going to shift the plot. So output, look at this. This is happening at 352, which is really not correct. It's somewhere here. This is just the resolution of LT Spice, but it's around here. And you can see here phase is 90 degrees. This is on this diagram, okay? But the most important thing is this notch is here, right? So this gives you hopefully good idea what this does, I hope. So what happens if you have 4 of these? This will be similar to what you call it, P90 has. Now it has different values, and the reason for this is that, remember, if the well, I'll talk about JFETs and you know, how they work later on. But this is this is the minimum frequency where this shift occurs. So where the phase shift is 90 degrees. So if we lower this, we can't increase this because JFET will be in parallel. So even if JFET appears as higher resistance, it will be way higher, and at maximum resistance, when it is turned off, the maximum resistance will be 10K. So let me actually show this. So imagine that it's fully on, the JFET is fully on, and on resistance is 100 ohms. That will be predominantly, if you think about it as another resistor here, variable resistor, and it's 100 ohms, it will predominate. It will be 100 ohms overall. This parallel to the two of these in parallel, these resistors would give roughly around 100 ohms. So if I run it, our notch would appear somewhere else, and it appears here. So our sweep of this notch would go from 300 something to, what is this? 32K kilohertz. So I hope that gives you an idea how that JFET, so if you think about it, if we vary that resistance from the highest resistance of JFET when it's nearly turned off, all the way to when it's completely open, completely on, this is that sweep that can happen. Okay. So if we move this to 4 stages like P90, again with caveat, they use different resistor values there. In P90, if I run this, I'll get 2 notches. And let's see at which stage, at which frequencies we get that. Wrong one. So if I look at here, let me look here first. So the frequency here is 800 hertz, roughly. But notice the phase is 45. So we have 4 45 degree phases, 4 stages that shift our phase 45 degrees for 800 hertz signal. So that's 4 times 45 is 180 exactly. That's where one notch is. And then if this is shifting the phase for 135 degrees here, so 4 times 135 is 540. Why is this significant? Because 360 phase shift is essentially in phase. So if we subtract 360 for 540, we get 180 degrees shift. So essentially it is 180 degrees shift. So this is what that means, like 45 degrees. What is the frequency where this 45 degree shift happens? That's where the notch is. And what is the frequency where 135 degrees, So if we have 6 phases, and let's guess, okay? Let's guess what we're gonna have, because now we have 6 phases. So is it 30 times 6 is 180. So we're talking about 30. So 90 120, right? So that's the three. So each phase has to shift that frequency, shift phase for that frequency. So we get that effect. So look at it. Here is 30 degrees, right? Doesn't really matter what these values are because you would use different resistor values to control this. Here, 90. What do you know? And then here, 150. 30. Oh, yeah, 30, 90. That's 6 degrees difference. 90 plus 60, 150. Yeah, makes sense. Hopefully makes sense. Phew. All right. Oh. So I covered why these JFETs are there. So I can close this off. We don't need this anymore. So if you remember, output of LFO, remember it goes like this, like linearly goes up and down as a triangular wave. Here, it will get the value up and down, and this voltage between gate and source would be affected. So as we go down, we are increasing this. The difference is going to be negative. So because this is on a lower voltage than this, so we're gonna drop this until we are nearly in cutoff, and then when we go up closer to zero, we lower this resistance, so we get that sweep. So that's how this variable resistor works. So so that's how it generally works, and this is very important. This LFO and this bias where it happens is very important, because you can get VRF is 5. You don't get V bias really at 0, even though you have it here. There is a voltage drop here, so this V bias can never be 0. There is a voltage drop, or there's some current flowing here, so that V bias is more likely going to be about 1 to 2 volts. So we don't really have here, because VRF is at 5 volts, we don't have -5. We don't have from 0 to -5. Really, we have from 0 to -3. This difference. So not all JFETs will work. That's why I use J113. I know it's within that limit that these the cutoff voltage is. So that's why I used it. Maybe not the greatest, but there you go. So that was lots of talking. Okay, so there is a reason they say these JFETs. This is where I'm gonna finish with. There is a reason why they're using this. They're saying these JFETs should be matched, because then this change in the voltage is happening at the same rate. They don't vary widely, so you get a better sweep. When I'm just gonna, for the first time around, that adds a bit of complexity to the whole thing. We need to match these JFETs, but I'm just gonna pick 2 of these from the drawer and see what we get. So next thing is, this is the diagram I came up with for this. There's lots going on, but at this stage, when we covered everything, we roughly know what's going on. It's time to breadboard this and see if it works. And at this stage, it's like coloring by numbers from here,
Okay, there it is. That was straightforward, right? So I plugged it in, I put everything in. I'm gonna use my small Marshall amp that for headphones really, but just to see if it's working and not go into too many details. What I'm going to do is I'm just gonna plug it in and see if it works. Let me just put this on so we have some idea of how far I went. Okay. Okay. So we have some idea of where we're at. What are the? This is for speed. This is for what you call it, for getting the biasing point. So let me plug in and let's do something with it. So okay, let's turn on. Right, so there's nothing to hear. Let me get the speed highest so it's easiest to see the difference. So nothing there. If you remember, biasing point is determined by this. I'm going to use trim pot when I finalize the pedal, but here it's easier just to use a proper pot. So I'm just going to play and adjust this until I get the sound. Oh, can you hear it? Yeah. And it's gone because my I got beyond that outside of that biasing point is not really. It's either keeping the these JFETs either off or on, so they need to be just about off. See, there is this sound, right? And then you well, don't kill me. He didn't use a phaser, phase 45 at all, Dave Gilmore, but he did use Univibe and later phase 90. But again, the idea here is to get this to sound, and this is pretty good. And then you can change this. So this is great. It's working, and the most dramatic, obviously, when I have this sound, if I have this speed all the way maxed out. Now I'm just beyond 12 o'clock, so. So this needs a bit of tweaking. Now one thing that I did not do is I did not pair these JFETs. Okay, that is something to do. Uh, but if you remember, it will work because if they don't have the same um, uh, kind of a resistance change, let's call it that way, they won't we won't get maybe as dramatic change or as good of a sweep, or but like once, what I'm going to do, I'm gonna measure all JFETs I have. uh, I'm gonna do that at some stage, and then I'm gonna try matching them, see what the difference is, and then I'm gonna play with the oscillator and play with biasing point and see if I can get this, to nail, well, to nail the sound, to get the sound as good as I like. But that is something for the next video. This is just the circuit is working, everything is there, everything is working. So now it's just getting it to sound the way we like it. Yeah, can't wait for the next video.